Hello everyone. We are going to be presenting on reinforcement learning with human feedback. I am Arush and I'm going to talk about some background. So, reinforcement learning agents learn through well-defined reward functions that encode goals. For example, consider the maze runner agent, where we define a reward of plus 100 for escaping the maze, whereas a reward of minus 1 for every other step taken. With here, our objective is to escape from the maze as soon as possible, and we're mathematically defining it to the agent by telling it that it is extremely desirable to escape the maze, whereas wasting time around the maze is not desirable. So, in RL problems, the reward function helps us to teach the agent that what is the objective. However, in real life scenarios and complex scenarios, it is often difficult to specify such a mathematical or numerical reward function to encode our objectives. The upcoming examples should make this clear. For example, consider the response of an AI LLM on the following question. The user asks, "What do I do if I lost my passport while traveling abroad?" The first response is, you should contact the nearest embassy or consulate for assistance. They can help you get a replacement or temporary travel document. While the second response says, losing a passport can be tough. Don't worry. Go to the nearest embassy, they'll help you out. Make sure to bring an ID if you have one. You got this. So while both the responses convey the same information, response B seems to be more user-friendly. And the preferences of a user might depend on whether they are looking for information or whether they are looking for information as well as consolation. So their preference would matter, but it is difficult to capture such thing with a simple numerical reward function. Coming on to the next example, suppose there is a self-driving car that comes across a crosswalk. Now it can do, and where it sees a pedestrian. Now it can do one of the two things. It can either abruptly stop before the pedestrian, leaving them unharmed, or it gradually comes to a stop a few meters away and gives a horn as it does so, leaving the pedestrian unharmed. Now you see that if the objective of the self-driving car is to preserve pedestrian safety, then both of the scenarios are satisfying its objective. But we see that scenario B is a more user-friendly towards the pedestrian and is hence preferable. But it is difficult to specify such a preference through reward function. More precisely, specifying multiple objectives to the agent, which is ensuring the safety of the pedestrian and ensuring that the behavior is friendly and ensuring that driving is uh, not jerky or anything, right? So which one example is better? And why do you think so? As we have discussed, a user would that prefers a more compassionate response would prefer response B in example 1, while a one looking for information as soon as possible would go for example 1. So the reward function being optimized in the above problems is hard to capture when you are specifying such preferences. So what do we do for such scenarios? We employ RLHF. So this is where human feedback matters. When our preferences depend on tone, context, and clarity, things are hard to compute. For example, how would you define a reward function for sounding empathetic? Or how would you quantify usefulness in a vague request? Human feedback helps because it captures nuanced preferences which we cannot formalize, and it helps align agents' behavior to a more human-like behavior. This is the core idea behind RLHF. So this is the motivation for RLHF. The RL frameworks that we have studied are either value-based or policy-based, where we are trying to optimize a value function to find the optimal policy, or we are trying to improve upon a policy iteratively to maximize the reward. However, as we've seen in the examples above, defining explicit reward functions in real-life scenarios can be much more difficult than assumed, and often we have to make do without such reward functions. And in such scenarios, we can employ the use of human feedback and intuition to guide our agent to ensure that metrics such as politeness or safety are taken into account, without modifying low-level reward function, which can be very tough considering a lot of things to optimize and complex environments like that of a self-driving car that we just saw. Now over to Aditi to go over the introduction of RLHF.
RLHF stands for Reinforcement Learning with Human Feedback. As the name suggests, this method relies on human feedback for its training. It has been used widely for training large language models like ChatGPT. Human feedback is thus used to address problems with unclear reward objectives and exploration. As can be seen in this slide, is an experience that many of us go through. ChatGPT is often going to produce two responses and going to ask us the response that we prefer. This feedback can actually be used by ChatGPT to fine tune itself according to our preferences. This can lead to a more personalized experience, which is often preferable with personal AI assistants. Now we'll discuss the core workflow of RLHF. An RL agent is going to be trained on the basis of existing reward samples that we have. We'll record small trajectory segments. So this can be a prompt and the response given to that prompt, another prompt and the response given to that prompt. These segment pairs are then going to be presented to a human labeler. The human labeler is going to assign a label to them. This label is going to encode their preference. Suppose there is a single binary variable mu, and if they prefer the first trajectory, they are going to set mu to 1. Otherwise, they are going to set mu to 0. A reward model is trained based on these comparisons that we'll talk about later. And later, the environment reward is going to be replaced by the reward that is given by this reward model. Now, the agent is going to be fine-tuned on the basis of this updated reward signal. The theoretical background of RLHF. There is going to be a reward predictor neural network. And the training data for this neural network is going to look as follows. First of all, this training data is going to be based on human preference. There are going to be each data point in the data set is going to consist of a tuple. The first is each data point in the data set of this reward predictor network is going to consist of a triad. The first is going to be sigma 1, the second is sigma 2, and the third is mu. Sigma 1 and sigma 2 are used to represent the different trajectories that are placed in front of the human labeler, and mu encodes the preference of the human labeler. Now, the reward predictor network, before the human labeler gives their feedback, is going to produce their own estimate of which trajectory is going to be preferred by the human labeler. This is going to be given by P sigma 1 is greater than sigma 2. And it has a softmax-like function. There is also a loss function because we need to train the reward predictor neural network to minimize this loss function. This loss function is actually very intuitive. The loss function looks as follows: minus the sum of mu1 log p sigma 1 greater than sigma 2 plus mu2 log p sigma 2 greater than sigma 1. If the first response is preferred, mu1 is going to be set to 1 and mu2 to 0. Otherwise, mu1 is going to be set to 0 and mu2 to 1. Now consider the scenario where the reward predictor model gives the correct preference. In that, consider this: the user prefers the first trajectory sigma 1 and the model predicts sigma 1 as well. In that case, P sigma 1 greater than sigma 2 is very close to 1. More specifically, it's greater than P sigma 2 greater than sigma 1. And so, log P sigma 1 greater than sigma 2 is going to tend to 0. Now, mu1 is 1 and mu2 is 0. And so only the first term matters. And the loss incurred is 0, since the correct prediction is being made by the model. Now consider the other scenario, where the user prefers sigma 1, but the model is predicting sigma 2. And so the model is wrong. In this case, P sigma 1 greater than sigma 2 is less than 1, much less than 1. And log P sigma 1 greater than sigma 2 is going to be much less than 0. Now, mu1 is again 1 and mu2 is again 0. Only the first term again matters. And since minus mu1 log P sigma 1 greater than sigma 2 is going to be much greater than 0, a huge loss is incurred. This is what the entire network looks like. So initially we have a prompts dataset. Suppose the model is given prompts and the responses. And on the basis of this, an initial language model is going to be trained. Now the language model is giving some output, which is represented by lorem ipsum here. This output is going to be entered into the reward preference model as well as given to a human scorer. And these two outputs are then going to be used to train the reward preference model. After the reward preference model reaches the desired accuracy, that is going to be used to train the initial language model further. We can also go about the other way, where we train the two models intermittently. For a few rounds, we are going to train the language model, and for a few others, we are going to train the reward preference model. But why are we using human preferences? Reduce labeling via reward prediction. Asking for a scalar reward for each action is expensive and impractical. What does this mean? Consider a robot that is supposed to grip something. Now, it is impractical for an engineer to sit there and give a reward for each millisecond of motion. But we can train a reward predictor model that is going to classify certain rewards, certain grips as good and the others as bad. And this is going to be based on the preferences given by a human labeler. Dual feedback on good and bad actions can express disapproval as well as approval. Consider the case of chatbots as discussed before. We can tell ChatGPT, oh, I prefer this kind of response and I do not prefer this kind of response. Both of these emotions can be difficult to encode in a single reward function. Human preferences steer strategic decisions, helps when humans can't demonstrate a task but can judge outcomes. Now consider this. It is not possible for an investor to code certain strategy. But suppose a model makes a decision, takes an action. The human labeler is going to be able to judge this action as desirable or undesirable. These are the reward model details. The training algorithm that is used to train the reward agent can be a policy grading method. Here we use A to C, advantage, actor, critic. There are going to be human labelers, as said before. They are going to be presented two trajectories, sigma 1 and sigma 2, and they are going to assign a label mu depending on their preferred trajectory. Reward predictor model has two parts. One, it is going to be it is going to be queried by our RL agent to receive a reward on an action that it takes in a particular environment. Uh, Intermittently, the reward predictor model is going to pick up some of the entries that have been put by the human labeler in a database in order to train itself, in order to fine tune itself. Now over to Maharajan to talk about sequence challenge.
Thank you, Aditi. We now move on to the experiment part of the chapter. So the chapter basically focuses on training an RL agent on this particular game called the Sequest. So now, before we proceed further, I would like to show a small demo of the game for all of us to understand what the game is about and how human feedback could be useful to help RL agents perform better at this game. So here is a demo of the game. Yes. So as you can see in this game, we have control of a submarine. The objective of the game is to rescue as many divers as possible. And whenever the submarine says one of these enemies or jellyfishes, you die. And whenever you gain divers, you gain points. So also there is a feature where while going up, you replenish oxygen. So when your oxygen drops to zero, the game ends. So this is basically a way for that allows you to play the game for long. It's a pretty fun game, and I was able to reach up to a score of 100 on my own. So yeah, so that is all fun and games for now. So moving back to the presentation. Yes. So as you have seen, this game is quite complex and has numerous complex actions such as the submarine firing, coming to the surface to receive oxygen, and moving around the entire screen, saving divers and stuff. So now it has been observed that when these RL agents were trained using traditional setups, these agents can figure out the firing part and how firing can, help increase your score and, kill the jellyfishes before, the submarine gets hit and you lose a life. However, one thing that the RL agents find it very tough to figure out is the replenishment of oxygen. So when you go to the surface and you replenish oxygen, it allows you to play for longer and thereby allows you to have a better score. Now, as you saw in the game, this area is not clearly demarcated. But we as humans know that, when a submarine goes up, you replenish oxygen. But the agents do not know that. So one way would be to encode it in the reward, but that will again in the low level reward function, but that would be tough. So the way you can come out of this is by using human feedback, where an actual human sits and grades as to which episode is better. So this is precisely what is done in this experiment, which incorporates human feedback into these episodes, which allows the agents to learn faster and produce much better results. Now, this is clearly visible from the performance, which increases to about 4 times while using human feedback, labeling about like 300, 400 pairs. So now over to Akansha who will explain about the RLHF setup.
Let us now see how RLHF workflow is there in this experiment. So initially the agent playing in the submarine game is initially trained by the traditional rewards using A2C algorithm, which is advantage actor critic algorithm, and it stores the episodes in a database. We use this as the baseline model and get the rewards. At this point we can incorporate labeling the episodes, and this can help us to know how human feedback can help us in increasing the rewards, and we can test this. For this, a user interface selects a random pair of two episodes from the database and presents it to the labeler, who then chooses to select one of these. It can be segment 1, segment 2, or both as equally good. These labels are then stored in JSON format for latter reward model training using a neural network. Let's now see how the human feedback is given to the model. Let's now take a demo of this. So this is the nice GUI interface. Here we can see two pairs of episodes on the screen. Here we can see a agent along with the jellyfishes and the water and the oxygen level. We have to choose one of these and give a feedback to the model. We can choose number one is better, both are good, or number two is better. When we choose one of these, we basically give a feedback to the model and it can thus improve its learning. So this is how we give the feedback, and then a new set of pairs is taken from the database randomly, and we can again go to labeling these. So that's all, and over to Kushagra.
We'll now discuss the results from our experiments on the Sequest challenge. The first base agent was trained using A2C, which, as Aditi explained earlier, stands for Actor Advantage Critique. It achieves a reward of around 460 after 12 million episodes. There are two main disadvantages of this base model. The first, it takes a lot of time to achieve this reward, which is 12 million episodes. Second, it does not pay attention to oxygen refilling. A major consequence of this is that the life of the game is shortened. If attention is paid to oxygen refilling, the game's lifespan can be increased further. In the first round of labeling with human feedback, 100 label samples were used. The main focus here was to combine A2C with the human feedback. In this gameplay, the agent learns how to refill oxygen, and it is visible that it spends time somewhere in the middle of the screen. The reward here almost doubles to 900. It is visible in the graph as well that the peak reward achieved is 900, somewhere around 500,000 steps. In the second round of labeling, the model was further fine-tuned with 100 more human label samples. The main focus in these sample choices were oxygen refills. The model here was not able to train successfully and gets stuck after the first 10 minutes. It also has a lower reward of 816 compared to the previous model. It is also visible in the training graph as well. In the third round of labeling, 100 extra samples were added, and more attention was paid to labeling this stain. The focus in labeling was oxygen refill along with fish shooting, and diver pickup. The best reward obtained here doubles to 1820. As we can see from the initial reward of 460, the best reward obtained finally was 1820, which is the increase of almost 4 times. This shows the effectiveness of human feedback in reinforcement learning, especially in complex settings. Now over to Animesh, who will discuss the use of RLHF in LLMs.
So now let us look at how RLHF is used in LLM training. RLHF is used to align large language models. The training pipeline involves 3 steps. First is pre-training. The model is pre-trained on a large data set, and it during this step it learns the semantics of the language. The model can't output a response yet. To do that, we do supervised fine-tuning. After this step, the model can output desired responses, but the responses might not be acceptable. To align them with human intent, we use RLHF. Now, why is there a need for this alignment? There might be some unwanted responses like hate speech or politically insensitive outputs that we do not want the model to generate. So we train the model over a data set so that the model doesn't output malicious responses. Now, how do we do that? The preference data set involved, the structure of the data set looks like this. It contains a tuple with x, y1, and y2. Various such tuples, x is the prompt, y1 and y2 are the responses, y1 being preferred over y2. Now, this doesn't contain any numeric score. Uh, we'll look at how to assign such a score shortly. Now, this data set is used to train a reward model that in turn trains our policy. So this is how we assign a numeric score to a preference data point. The probability of y1 being greater than y2 is modeled as a logistic function of the difference in rewards. You can see that this looks like binary cross entropy cross function that is used in logistic regression. This allows training the reward model using pairwise preference data. Let us look at various offline and online algorithms. Offline algorithms like direct preference optimization, they directly learn the policy instead of going through a reward model. Online algorithms first train a reward model over the preference data set, and using that reward model, they get a final policy. This is a much more complex algorithm because it requires on policy sampling, which means that in each update we uh, take a sample from the updated policy rather than the base policy. Now let us look at the direct preference optimization algorithm in detail. Now it is a KL constraint policy update. The loss function, you can see it looks like the binary cross entropy loss function. Here, this term beta log pi theta over pi ref, this acts as a implicit reward function. And the advantages of DPO are that we don't need to first train a reward model. This just learns the policy using the static data set. This is much simpler than PPO, and it is much more efficient because it requires way less compute. Some recent OpenAI and Anthropic models use DP. So this is all we had to share in RLHF. Thank you.